Thousands of wildlife species call the Everglades home, but one species is unwanted and taking over.
These helicopters flying over Florida's Everglades are doing something you would never expect. They are dropping millions of dead mice straight into the swamp below. But this is not random dumping. Each one is filled with a chemical designed to kill one of the most invasive predators in the world, the Burmese python, a snake that has already silently taken over huge parts of Florida. But here is where it gets extremely serious. While it has proven to be one of the most effective solutions so far for controlling Burmese pythons, there is a terrifying catch. Scientists warn it could trigger a chain reaction that can put the entire ecosystem at risk. So is this really a solution, or a new problem being created inside the swamp? Let's get into it. A swamp being eaten alive. The python problem started in the late 1970s and 1980s, when a few Burmese pythons were released or escaped from the exotic pet trade. But over time, they didn't just survive here, they spread fast, deeper into the wetlands than anyone expected. Today, no one can even agree on the exact number anymore. Estimates range from around 100,000 to over 300,000 pythons living inside Florida's wild wetlands. That is not a small gap in data. That is uncertainty on a massive scale. And the reason is even more disturbing. These snakes are almost impossible to find. Scientists use something called detection probability. For most wildlife, you can track and estimate movement fairly reliably. But for Burmese pythons in the Everglades, the detection rate is estimated at under 1%. That means even trained experts may only find one snake out of every 100 actually hiding in the marsh. And the ones that remain are not small. Some grow beyond 16 feet in length and weigh over 150 pounds. The largest one ever captured in Florida reached 215 pounds. When scientists opened it, they found something even harder to process: 122 developing eggs inside a single female. One snake, one body. That much future life already forming inside it. And this wasn't an exception. A healthy female python can lay more than 100 eggs in a single breeding cycle. And she doesn't just leave them behind. She coils tightly around the nest, guarding it constantly. Even more unusual, she generates heat by contracting her muscles again and again, keeping the eggs warm until they hatch. In this environment, that means survival rates are extremely high. Now, think about what that means at scale. Even if only a few thousand female pythons are actively breeding in the Everglades, and each one produces around 100 eggs in a cycle, that already turns into hundreds of thousands of new snakes entering the system every single year. And what they are doing to native wildlife is already visible in the data. Raccoon populations have dropped by 99.3% in core python zones, opossums by 98.9%, bobcats by 87.5%. In parts of the Everglades National Park, marsh rabbits and fox squirrels have completely disappeared. Not reduced, but almost erased. And this is not random hunting. These snakes are reshaping the food web itself. A full-grown python can swallow a deer whole. Even alligators have been found inside their stomachs in rare cases. This is no longer just an invasion of one species. It is a replacement of an entire predator system, happening slowly enough that most of it remains as unseen. And that raises a question no one can avoid anymore. If the problem is this large, this hidden, and this advanced, why has nothing been able to stop it so far? Hunt that never catches up. For years, Florida has been fighting this problem with everything it has. The two main agencies leading the effort, are the Florida Fish and Wildlife Conservation Commission and the South Florida Water Management District. Together, they run one of the most expensive invasive species control programs in the country. And at the center of it is something called the Florida Python Challenge. It sounds like a breakthrough event. Nearly 1,000 participants from across the world dropped into the Everglades for 10 days, all trying to hunt Burmese pythons. Cameras, publicity, competition, everything. But when it ends, the numbers tell a very different story. Usually, the entire event removes only around 100 to 150 snakes. Hundreds of people, days of searching, and the result barely moves the scale. Outside this event, Florida also pays around 100 trained contractors who work all year long. These are not casual hunters. They are paid, vetted, full-time field trackers. They are paid hourly just to look and then rewarded per snake. Around $50 for a small one, more for larger snakes, and even a bonus if they find a nesting female with eggs. Millions of dollars flow into this system every year, and yet the outcome barely changes. These contractors remove around 2,000 to 3,000 pythons annually. That sounds like a large number until you compare it to estimates of up to 300,000 snakes hiding in the wild. It barely scratches the surface, and the efficiency problem is even worse. On average, it takes 12 to 30 hours of searching in the field to find just one python, one snake after an entire day of work. So the question becomes unavoidable. Why is it so difficult? It isn't just effort, it is structure. Pythons do not follow predictable paths. They have no fixed territory like most animals. They move silently through water and sawgrass for miles without leaving tracks, scent trails, or visible patterns. The Everglades itself makes it worse. Dense sawgrass, deep water, and unstable ground turn large areas into places humans simply cannot enter safely. And even when a hunter is close, the snake often isn't seen at all. Its skin blends into the moving grass so perfectly that even direct sightings can fail. At this point, it wasn't really a hunting problem anymore. It had become something else entirely, a detection problem. And when scientists finally accepted that reality, they reached a breaking point. More hunters, more money, more time, none of it was changing the outcome anymore. So they started thinking differently. Not like hunters, but like something else entirely. Something far more experimental. And the solution they came up with was so unusual, it didn't sound like wildlife control at all. But before that idea could even make sense, there is a warning from history that changes everything: the Guam disaster. To understand why scientists eventually started considering such unusual solutions, you have to leave Florida entirely and travel nearly 8,000 miles across the Pacific Ocean to a small island called Guam, because Guam had already lived through a version of this nightmare. In the years after World War II, a species called the brown tree snake accidentally arrived on the island, most likely hidden inside military cargo shipments. At first, nobody paid much attention. It was just another snake. But Guam had one major weakness. For millions of years, the island had evolved without native snakes. The local birds had never faced a tree-climbing reptile predator before. They nested on low branches, laid eggs in exposed nests, and had almost no instinct to fear a snake moving toward them. For the brown tree snake, Guam wasn't an ecosystem. It was an unlimited food supply. As the snake population exploded, the damage became impossible to ignore. Bird populations began collapsing across the island. Species that had survived there for thousands of years suddenly started disappearing. By the 1980s, entire forests had gone silent. No birds singing, no nesting calls, no movement in the trees. Scientists later estimated that around 10 to 12 native bird species were lost from Guam's forests. Some survived only because conservationists managed to keep small captive populations alive. They started using power lines like highways. Every year, they caused dozens, sometimes hundreds, of major electrical outages by short-circuiting the grid. Schools lost power. Hospitals lost power. Entire communities were affected. The economic cost reached millions of dollars annually. This is what happens when an invasive predator wins completely. By the 1990s, the situation had become desperate. Traps weren't solving the problem. Search teams weren't solving it. Detection dogs weren't solving it. In some areas, snake densities reached astonishing levels, with thousands packed into a single square mile. Scientists needed something entirely different. So they started testing different chemicals, looking for a biological weakness in the snakes that could be used against them. And during those experiments, they stumbled across something nobody expected: a common painkiller, the same kind sitting in medicine cabinets across America. Even a small dose of it could shut their system down within days. At first, it sounded almost impossible to believe. A basic medicine turning into something powerful enough to kill an invasive predator hiding deep inside forests. But what they discovered next wasn't just a warning. It turned into one of the most powerful weapons ever used against snakes. The crazy solution. When scientists were testing different chemicals against the brown tree snake, they found something unexpected: a common painkiller called acetaminophen, the same substance found in ordinary medicine cabinets across the world. At first, it didn't make sense. In most animals, acetaminophen is relatively safe in small doses. But in brown tree snakes, the reaction was completely different. Their bodies cannot process it properly. Instead of breaking it down, it disrupts how oxygen is carried through the blood. The snake gradually becomes weak, loses coordination, and within a short time, its system shuts down. Even a small amount can become lethal. That single discovery changed the direction of research. For the first time, scientists had found not just a way to trap the snake, but a chemical weakness inside its biology. But the problem was still enormous. How do you deliver it into a landscape where snakes are almost impossible to locate? So researchers at the USDA developed a delivery system built for the air. They used dead, frozen mice as bait. Each mouse was attached to a small cardboard piece and long strands of lightweight material. When dropped from helicopters, this setup slows the fall and allows the bait to catch in the upper branches of trees instead of dropping into water or mud. That detail is critical. Because brown tree snakes are not purely ground animals, they climb trees, hunting birds, and small animals in the canopy. So the bait is placed exactly where they naturally search for food. In field trials carried out in Guam, thousands of these bait units were dropped over controlled forest zones using automated aerial systems. After repeated deployments, monitoring showed something striking. Snake activity dropped by around 80% in targeted areas. And when scientists saw it working at that scale, they immediately considered applying it to Burmese pythons in Florida too. But when they tested it further, they found a biological limit. Adult Burmese pythons grow too large for this approach to work effectively. Their diet shifts toward large prey like deer, and they no longer rely on small rodents or tree hunting in the same way. But on smaller pythons, especially juveniles, the story is very different. Young pythons are highly active in trees. They climb through branches, hunt small birds and rodents, and constantly search for food in the canopy. That behavior makes them far more likely to encounter the bait compared to adults. And that is exactly why the method seemed promising. It targets the vulnerable early stage of the snake's life cycle. From there, the idea began spreading quickly in scientific discussions, because on paper, it looked like a way to cut the population off at the root, stopping new generations before they could grow into full-sized apex predators. But once scientists looked at it more closely, they realized something uncomfortable. At large scale, this wasn't just a targeted solution anymore. It was a high-risk intervention inside a living ecosystem. The ecosystem danger. In a few controlled test zones, researchers started seeing something that looked almost like success. After repeated bait drops, python activity in certain areas reportedly fell by nearly 80%. For the first time in years, it seemed like there might actually be a method capable of slowing the invasion instead of just reacting to it. After so many failed attempts, this felt like a breakthrough. But almost immediately, another set of problems began to appear. Because the Everglades is not a closed system. It is a connected water network where everything is linked. And once a chemical enters it, it does not stay in one place. The first concern comes from timing. Even after a poisoned mouse is eaten, the chemical does not disappear instantly. It takes time to act, and during that time, the animal becomes slow, weak, and disoriented. That makes it an easy target for other predators, which means the toxin can move from one animal to another through the food chain. Then comes the canopy risk. The bait is designed to hang in trees, which is where young pythons hunt. But those same branches are also used by birds of prey like owls and hawks. With extremely sharp vision, they can spot movement from a long distance and easily mistake a struggling mouse for normal prey. Unlike many other animals, raptors are highly sensitive to this compound. Even small exposure can lead to severe internal damage, affecting the liver, blood system, and coordination. In nesting birds, this risk becomes even more serious because adults feed their chicks directly. But not all bait stays in the trees. Wind, rain, and decay eventually bring part of it down to the ground. And on the forest floor, scavengers like raccoons and opossums take over. These animals eat almost anything they find. In mammals, exposure to this chemical can cause rapid organ failure and severe blood damage, even from a single contaminated meal. And that is where the concern becomes serious. Because while all of this might sound like a manageable risk on paper, a closer look shows it may be far more dangerous than it first appears. The loss that can't be recovered. As the risks of the bait system became clearer, one concern stood out above everything else: the impact on Florida's most fragile species, the Florida panther. Today, there are only around 120 to 230 individuals left in the wild. A number so low that even small losses can push the species closer to collapse. And biologically, the risk is severe. Cats have a unique limitation in their liver. They lack key enzymes needed to safely break down acetaminophen. Because of this, even small exposure becomes highly toxic. It quickly damages red blood cells, reduces oxygen flow in the body, and leads to rapid organ failure. Now consider the environment. Panthers do not usually hunt mice, but they are opportunistic. They will scavenge when food is available, especially fresh kills. And the bait system places poisoned carcasses directly in the same regions where panthers move, rest, and hunt deer. That overlap is what makes the risk so serious. Not because panthers actively target the bait, but because they cannot fully avoid it. And then there is another species that changes the entire equation: the eastern indigo snake. It is the longest native snake in North America, reaching up to 9 feet. More importantly, it is one of the only native predators in Florida capable of actively hunting juvenile Burmese pythons. But its survival strategy puts it directly in danger. Indigo snakes feed heavily on rodents, including mice. If they consume a poisoned bait mouse, or even eat a weakened python that has already ingested the chemical, the toxin enters their system immediately. Reptiles lack the biological pathways to process it safely, making exposure highly dangerous. So the system becomes more complicated with every layer. Because what is being tested is not just a way to reduce python numbers, it is an intervention that touches some of the most sensitive species in the entire ecosystem. And that leads to a difficult question. If a solution is finally starting to work after years of failure, but it also puts endangered panthers, native snakes, and the entire ecosystem at risk, then the real question is, how should it actually move forward? And what does the future of this decision look like? What happens next? Looking at this problem, scientists often compare it to a completely different case in Australia. There, invasive pests like foxes and feral cats are controlled using a chemical called Compound 1080. But what makes it work is not just the poison itself, it is the environment. Many native Australian plants naturally contain fluoroacetate, a similar compound. Over thousands of years, native animals developed a natural tolerance to it. That means the poison is deadly to invasive species, but far less harmful to many native ones. And that is the key difference. Florida does not have that kind of built-in biological safety net. So a broad chemical approach there does not separate target from collateral in the same clean way. And that is exactly why the debate over acetaminophen bait drops becomes so difficult. Because unlike Australia, there is no evolutionary buffer protecting Florida's native wildlife. At the same time, real-world efforts are still continuing. Detection dogs are being trained to follow python scent through thick marsh areas. Judas snakes are also being used. These are actually male pythons that are tagged and released back into the wild. They then move around naturally and lead researchers straight to hidden breeding groups of snakes. Scientists are also testing pheromone traps that lure pythons using chemical signals instead of food. And in the background, genetic tools like gene drives are being studied, though they are still far from real-world use. But even together, these methods have one clear limitation: they are small-scale. They work in specific zones, on specific snakes, in specific conditions. None of them can yet cover the vast, unreachable landscape of the Everglades. In the end, we have to accept that Florida is now fighting an invasive crisis with no perfect answer. And that leaves two questions. Should the government keep testing newer and newer solutions to finally solve the python problem? Or should they stop experimenting too aggressively to avoid putting native species at risk? What do you think is the right path forward? Let us know in the comments below. If you enjoyed this video, don't forget to give it a thumbs up. And if you don't want to miss more incredible stories like this, make sure to subscribe to the channel. We'll see you in the next one.